Hello, here's Malban again, and again I'm going to talk about Vide. In this case, Vide 2.0. Once you downloaded Vide 2.0, you will probably see a difference right away because I changed the look and feel of Vide. If you prefer the old look and feel, you can configure it to the old look and feel if you want to using configuration. You go to Tools, Configuration, and the saved configurations of an item old default, and you can load that and it will look like the old one, but for the moment at least I prefer the new style, so I load the new default again, and it's a darker theme, as you might have noticed. With Vide 2.0 there are a couple of differences. Two main differences are the display routines, which are now using OpenGL, and the support of the language C. I already did, I think, a YouTube introduction to the OpenGL display, so I won't do that again. The default is now OpenGL. If you do not want it as default, you can always go to the configuration, display, and switch joggle on or off. Obviously, if it's on, then the new display routines are default. I'm doing this video with a beta version that is not yet available. I'm at 2.0 alpha 08. They are all very small errors, mistakes, bugs that can be corrected, and I hope when there is finally a 2.0 final, that most of the bugs will be crushed and that you can use it as I intend Vide to be used. Of course, this also needs some user feedback, so if you discover any errors, bugs, or things you don't like, just mention them to me via, I don't know, JIT or ProBoard, or on my pages, blog comment or whatever, so I may have a chance to correct things. Anyway, once you downloaded Vide 2.0, whatever other version it is, also the C binaries are within Vide, and from my experience you might have to check if the C binaries are actually executable. I'm packing Vide usually with a zip program, WinZip, and I experienced that sometimes not all file attributes are set correctly. I myself am working on a Macintosh environment. I tested Vide 2.0 and all C functions with Linux, with Windows, and with Macintosh. And you might, as I said before, look at the file settings. So this is the first thing I will show you. I'll switch to some sort of command window and show you where the files are located. So this is the actual Vide directory. Wherever you unpacked it, the directory will probably look nearly the same. There's a new directory that wasn't there before, simply called C. Within this directory, all binaries for the C supporters are located. And if you go into this directory, there are directories Linux 32, Linux 64, Mac, and Windows. Windows executables are always executable, so you don't have to check the flags there. If you're on a Mac environment, please go to the Mac directory and into the bin folder and check if there's in this case, a little X for the executables, or you might want to change them with whatever tools you use. If you're a command line, you should probably use change mod and, I don't know, 777 or something like that. Or if you use a tool like me, this is actually the mu commander right click and well, in English it's probably attributes or something like that, and there you go to German ausführen, or executable flag must be set. So this is for Mac, and for Linux it's the same. There is a bin directory with the same binaries actually, and for Linux 64 also. So please check that if you intend to use the language C within Vide. As some of you may know, about 20 years ago I did another C package for the Vectrex, and the new package is not built on the old one, but rather on the one that was done by Professor Dr. Per Johansen from the Pforzheim University, Germany. He provided most of the C setup I'm using, and it's actually working quite well. Not always the most performant version, but I haven't discovered many bugs in any way, and the two bugs that are known were discovered by Per, and I documented them within Vide. You might want to look at that, and perhaps I show it later. I don't know yet. Anyway, the examples I did for my last package about 20 years ago were about 8 different demo programs. I ported them to the new Vectrex C. Also, all available C programs I've found in the internet for the Vectrex I also ported. So within the projects directory there are now demo 1 to demo 7. A thing I called load runner. It's no load runner, don't worry, but for some reason or another I called it that. That's actually demo 8 from the old one. Then the new demo from of mine, demo 3D, which is more or less based on demo 7. And Blocksorgs is a program written by Frank Busse, which is also well known for the Vectrex. It's a C program. I ported it to the current C version. Also Scala Ownage, I have to look from whom that is. That was Sebastian Mihai. And the last one, Vecpong, also C source code provided, was done by Flip, oh ye, the pronunciation, Riscombe Burton, I think, or something like that. So these are all, to me, known C programs, and they work with Vide right out of the box, and you can try them. They are all in the project directory. You can load them and examine them. There are actually quite a few dozen in the meanwhile more C programs, but these are not available in source code. They were done by the students of the said Professor Dr. Per Johansen within his university courses, but as said, I don't have the source, so I can't actually show them to you. In order for my old programs to work, I had to convert them, because 20 years ago I think I was a little bit stupid. I changed all the BIOS names of the original BIOS, and also had a different calling convention. The usual Vectrex calling convention for coordinate is YX, and for some reason or another 20 years ago I did XY. So I changed all the sources accordingly, and now they work okay. I'll show them to you later. So for starters, I would like to start a simple C project and show you how that is done. As usual, if you want to edit or program something within Vide, you go to the Vectrex editor, Vide. It's under the tools sections, Vide. There's no project loaded, and you can go to the new button, click new project. The project dialog is more or less the same than before. You can give a name to your project, well, C project 1 with a large P, and I'll place it into the projects directory as usual. Now these options are new. The normal C project was a test of mine which, well, I did not finish, so this is always disabled. You can't do anything about it. If you want to do a C project, you have to switch it on using the checkbox Peer C project. This is what I do. All the other options are now disabled. The only thing you can still do is enable C debugging. I'll do that because I might show it to you or not. The main file is now empty. And if we press the create button, the project is created. Now this C project looks a little bit different than a normal assembler project. There's a whole directory structure built from templates, and these are the files that are copied to the current project. For you, mainly interesting directory is the source directory. There are for now 3 files. It's the main C file, the cartridge.c file, and the controller.h file. The project starts off with a simple hello world program. I open the C program and you see this is the main loop. Wait, recalibration, and print string hello world. You can execute that right away and see it running over here. This is the hello world program. So now a few words to the directory structure we are using. The current structure, bin directory. The bin directory will contain the final Vectrex executable file and the control file which contains debug information. This is the file actually the emulator will run. You also see it above here. The build directory, here all more or less temporary files go which are built during compilation. These are under the lib all S files, also assembler source files generated from the C code and many other files. And at the top, build project, the S19 files. This is a Motorola file format which are linked together to the final bin file I showed you before. Include directory and lib directory, I will say something to them later. Manual, this is a default PDF or PowerPoint presentation file, which actually looks like I open it somewhere. It looks like the actual Vectrex file that you can edit if you really want to do a whole Vectrex project included with all files. There's a little how you use that. Then there's an overlay directory with a default overlay. As you can see here, it's loaded directly from the project directory. You can change that. There's also a PowerPoint presentation file, and there are a couple of different default overlays you can use, or you should probably edit in some way. Also how to, and the note that they were done by Peer and so on. And the actual source directory I told you about before. So when you compile a program, all .c files under the source tree are compiled. Subdirectories are also included, and search for .c files, and all the C files are compiled to separate assembler source files, and these assembler source files are then assembled and linked to the final bin file. So you do not have to edit any make file or anything, just any .c file that is located anywhere under the source directory is compiled and actually linked. For convenience, we might get to that later. All .s files are also compiled. .s files are assumed to be assembler files. Assembler files not in, how should I call it, Vide assembler, ASCII, but for the assembler used by the C compiler, which is a different one. The C package pair provided uses a GCC C compiler and an assembler done by Alan R. Baldwin, which compiles the generated assembler sources. And from the same guy, Alan R. Baldwin, linker RSLink is used to link the generated binary files. This at the moment cannot be circumvented. I don't like it very much that there are two different assemblers used within Vide right now, but for now this is the way we had to do it. It may change in the future, but I don't know yet. You as just a user of C will probably not notice a difference. At least I hope so. When using the current C package, the main work that pair did to get it working can be seen in this small include line, include Vectrex.h. This actually includes all BIOS data you can use within C. You can use all BIOS functions with names that are compliant to the Bruce Tomlin BIOS disassembly. So if you know the BIOS disassembly of Bruce Tomlin's and its names, you can program right away in C. We will have a look at this file and I show you what Pierre did. Within Vide you can actually double click on include files and they will be open. So I'll do that right now. The Vectrex.h is built up of 3 different Vectrex include files again, which are called RAM, ROM, and RAM. RAM is all the RAM data, the BIOS RAM data that you might know from Bruce Tomlin's disassembly, with all variables the BIOS uses. They are located from the location C800 to C880. And also included are the VIA IO locations, registers, whatever you want to call it. So you can use these names as normal variables. You will see that later what I mean with that. The ROM are all ROM data. This is mainly the music pieces and ADSR tables and so on. These are the sinus and cosinus table, node table, and so on. These are fixed data tables, and the RAM are the actual BIOS routines that you can call. Pair sorted them, and here you can see a list of all the routines and some comments to them. As you see, the names are exactly the same as in the Bruce Tomlin's BIOS disassembly. Actually, later you might look sometimes at these definitions, because you will see what kind of parameters are used, what kind of signatures the functions really have, and the data types passed to the functions or returns. So you see, I don't know, .d wants to have a integer A, integer B as position information, which is actually Y and X, but they are called A and B because they are located, the final variables are located in the register A and register B. This is a convention pair that all variables are called by the register name their final destination is. All of these functions are marked with keyword inline, so all of these functions are actually inlined when you use them, which makes them a little bit faster. So another thing you might wonder is what the cartridge.c file is. The Vectrex binaries actually must have a certain structure, and the structure is G space GCC and anything following. The structure is generated by the cartridge.c file and is linked to the final output file, and thus the correct cartridge format is kept. The structure is given, well, in this definition, and you can enter your own game title and change the music and the string positions and width and height if you want to. So this concludes more or less the general section. I will show you a few C files now, what they look like and what can be accomplished. All of the files, or all the projects I'm showing you, are located in the projects directory. There is blocksorgs of Frank Busse. I'll open it. So the main file is a blocksorgs.c. This is actually the whole game. This is the main loop, which is more or less a state machine, and the definition of the blocks is in the block.i file. Frank, I think, generated most of the data, and it's not calculated on the fly. You can run it. It's actually a cute game, but it is only 3 levels. But anyway, I'll enlarge it a bit so you may see it better. Using the keyboard you can control this block over here, and the target is that you always have to well, go to the target. There are only 3 levels. The game is a clone of a game found in the internet. Look at the file for the location, and it's quite cute actually, I think. It's a little bit more involved. I won't do this level now. So then there is scalar ownage. Oops. A very small game done by Sebastian Mihai. It's sort of a little shooter. Press fire, and as you see, you can shoot the enemies above, and the level starts over again after clearing. And then there are about 8 or 9 demos, I think, that I did, from demo 1 to demo 7, and a thing called Load Runner, which isn't a load runner, and a 3D demo, which, well, is a 3D demo. Demo 1 is just a hello world. Demo 2, I don't know. One of them is a little Pac-Man that you can control with the joystick. Another one is playing different BIOS musics. And another one is a scroll text, which uses a assembler scrolling from Vectrex Frogger, including the bug that it's within the code. And then there's a YM file player with 9 different YM files. And well, what else is there? The Demo 7 is a short version of the old Demo 7 because I was a bit lazy. I did not want to translate all the 3D files. And actually the Demo 3D is a relative of Demo 7. I'll show you that one. It's a little project that I cancelled because, well, I haven't got the spirit left to do to finish it. It's actually what you hear in the background is a Arcos tracker file played from the sea, and this is a generated, well, landscape, or it's not landscape, but whatever you want to call it, and houses scroll from the back to front. You can actually change the perspective of the whole thing, and you can go left and right. Well, that's about all you can do right now. Well, yeah. Then there is a load runner, which actually also includes a couple of different things I did. First is the scroll text I mentioned from the Frogger. In the background, Arcos tracker file is played again. Then this is an animation and a vector list taken from Vectrex, included in the C file. I will show you later how to do that. This is actual game. Well, it's not finished. This is a little man you can control. And well, yes, that's about it. And one other thing, which one is it? I'm looking for a shot demo. I think it's 4 or 5. Can't remember right now. Just let's play it. There's one thing I want to show you. Nope, it's not. Then I think it's number 5. I call it shot demo because many shots are on the screen. Yes, that's it. As you see, these are 60 shots done in C, randomly generated, moving all over the screen. This is actually quite performant. It's in 50 Hz and 60 shots. I think that's quite good. But I used a trick, and the trick is that I did not use the default C settings. You can left-click the project properties, and these are the actual C flags that are passed to the compiler. And the default C options include no frame pointer omit, and the default options are not optimized. I remove the optimized option and run it again. Look at the speed now. It's below 30,000. Is that below 30,000? And if I compile it again with the default options, you will see a huge step upwards, and you can see that optimization with the compiler actually is worth it. And now the maximum is about 46,000. It's more than 30% well, additional wasted computational power of the Vectrex. And just with changing the options, you can actually very much improve your project. The only thing is that the options -03, which is the best optimization option available in GCC, and the omit frame pointer option, it's not guaranteed to work. At least at the moment, Per and I are working on optimizing the compiler settings and the call conventions and so on. Right now, most of the time, actually, I think the the omit frame pointer and the optimization options do work, but sometimes not. So we decided to leave the default at no optimizations and frame pointer. But you might want to gamble with it. So see, 46,000. Compile it again with advanced options, and now we are below 30,000 again. I think that's quite impressive, actually. So what I'm going to do now is start a little Vectrex project and do one or two things to show you how to, well, use C. New project. Actually, we did a new project, didn't we? Then we might as well load that project somewhere here. C project 1, main C. This is our hello world from before. This is a generated one that is the actual project template. First we give it a name. So we call it C project. And if you start that, you will see directly C project here. And what you usually do is print a vector list of some sort and not just the hello world. Also we need an intensity setting here because after some time this will go dark. A quick way to look up the Vectrex BIOS functions, because even I don't know them all and I always forget how they look like, is there's a directory actually I did not mention yet. It's a doc directory, and this is a short form of the bios.h files that Pear did, and they contain more or less just the names. These are not included, these are really for documentation only. So if you are now looking for a intensity A setting, how it's written exactly, we go here, search for intensity. That's what I always do, and at some stage some intensity is there. So this is intensity A, and you see here it's already getting darker. It's not good. So intensity A, full brightness is 0x7f, and if you start, you will see this is A brighter, and B, it will keep the brightness. So next thing is we want to print a vector list, and first thing for that is generate a vector list, and for that we usually use Vectrex. Here we have Vectrex, and I'm too lazy to draw a vector list now, so I just take one that I have already available. This is from Frogger, and we can export this one vector list as usual with different parameters. All different lists can be exported now. If you just export them, you see here this is generated assembler source code, but we can always also generate C source code if we check this checkbox C over here. Now you see this is a constant char vector list, and we also can name the vector list. We can call it caterpillar or something like that. Caterpillar. Oops. Caterpillar. Okay. Generate. It's called caterpillar now. And this is a default C format, which is well, standard C. I've got a second checkbox here. This is only used if the first C checkbox is always checked. If you generate now, we generate a Pear C source code. Pear has defined an own structure for use within his C source and for the use within his C classes. It's a vector list which actually is typed, and you can see here the type. This is a diffie type, the size of the vector list, and the vector list itself. Personally, I do not use it, but you can if you want. But well, I disable it again. It's not possible to generate runnable code with C. You can only do that from assembler, but you can generate vector lists and animation vector lists for C if you enable this C checkbox over here. So I generated a draw VLC compatible source, mark it, copy it, and I can insert the vector list here in our C file. So now it's a const signed char vector list. If it's const, it usually is placed within the ROM section of the cartridge data. If it's not const, then you can write to it, and with Vectrex this means it's generated into the RAM, and you usually want to use const for, well, constant data. Now we want to print it, and as mentioned before, where is it? Vector draw, there. This was a draw VLC. Now we search for the draw VLC function. Draw VLC, not found. Then we go backwards. There it is not. Somewhere it is. Draw VLC. So this is a draw VLC function as defined by pair, and it uses a void pointer. So we go here and oops, want to do that. Draw VLC and oops, take our vector list and the default C settings is warn all and quit on warning, or warning equals errors. So you have to be very careful, cast all things to the correct settings, otherwise the compiler will step out and tell you, hey, you did an error, even though it might only have been a warning. If you do that, I think it should work out of the box, but it's drawn, well, very small over there. Actually, it's not drawn at all, because a print string D, that is internal information, quits with a reset to 0ref, and reset to 0ref leaves the controller register of VIA with 0 enabled, which does not allow printing of anything other than the 0 point. So we have to insert a move. Where do we want to move our vector? Move to I always forget if there is a I think it's called this, move to D. Over there, this one we take, move to D, and we move to first the y coordinate. Let's say it's, I don't know, 50 and 0 to x, so it's a little bit upward. And we might want to have a scale factor also. Scale factor, also something I usually forget is how it's exactly called. It's this one here. This is scale. So this is the scale of the move. Let's say the scale of 0.80. It's a fairly high scale, and the scale of the actual drawing might be a little bit smaller. But I remember right now the vector draw function. These are really small coordinates. As you see, it's a 1, it's a 2, it's a 2. There's a 4. I think that is the largest coordinate. This is really small. I can you can compile it now, and you might see that it's really small. There. This is the caterpillar. A very small caterpillar. Even though it's drawn with a scale factor of 40. As usual, you can enable factors with your vector list. I do that and generate the vector list again. Now you see there's a blow up factor, and it's the define up here. I'll copy that again and use the define to enlarge our vector list. Remove, copy. So if you print that, it's exactly the same, but we can enlarge our vector list. It's just a blow up. You just have to keep in mind that the final result of the multiplication of all vectors must be lower than 127. So if we have a 4 here, we could go to a pretty high value. This up to doesn't matter. Let's say 40. Let's compile and failed error integer overflow expression. So 4 times 40 is 160, and this is larger than 120. What did I say? They are large vector lists. This is how you can print a vector list. So, next thing we might want to do is to add some music. There are different options to add music. It's a YM option, it's a AKS option, or the AKAS tracker. For now, let's add a YM file. For that, go to the project, add file. Now we have to locate some YM file on our hard drive. It will be copied into our directory structure to the main directory. You can download with Vide several thousands, actually, YM files, and they are located in the download directory, if you ever did that, from the configuration. Sound, YM, and here all the directories are. Brimble, Alistair, and I take, and Division 1. I like that one. So now the Division 1 YM file is copied to the project. Now you can choose the pop-up build Vectrex YM file. Do that. The YM file thingy comes up. I actually should call it YME or something like that. Never did. And you can create C players for it. So you have to choose create player, C output, and the only two supported, states also here, supported players is YM optimized speed and uncompressed. Uncompressed usually is, well, not really usable because uncompressed YM files are really big. Historic version, I did not do that because there were some bugs within it and it does not play also well. Optimized speed is a actually only viable export for C because streamed, I didn't do a stream player for C because the streamed variants that are generated for assembler, well, consider the input data and are different, actually, or might be different for every YM file it's generated for. And quite honestly, I didn't bother to do that in C. So the only YM option right now is YM optimized speed for C. You choose that, create source. Now you see within the Vide directory it is working, and after it finishes it prints something like, hey, I finished. And then a .s file is generated within the source directory, and a .h file is also generated, which contains the information we need to actually play the file. Yeah, YM files, large ones, are hard to pack. Register 3, well, only 10 more to go. Hard to believe I actually coded that about 20 years ago and it's still more or less working. Spock would say, fascinating. So, there, YM convert to Vectrex done. Now you see there are two files generated within the source directory. This is the actual source data of the YM file, of the packed YM file. This is in assembler code, and it's assembler code not compatible with ASCII, but with the RS6809 that I mentioned before. You should not edit that. The only thing you should or might do, if there are some YM files that have, well, quirky names, and the labels are always generated from the name of the actual YM file, you might have to search and replace the name if the YM file is called a funny name. But the compiler will tell you, hey, this is a stupid name, and produce many errors. So actually, you do not have to look at this file at all. Just that you know it is there is enough. The compile will we take this file, compile it, link it to the final Vectrex file, and everything will be okay. So now left to do is how to play this file. Now we come to the directories that I did not mention before. There's a lib directory and an include directory. If you place the cursor on the lib directory and call a pop-up menu, you will see different entries. For now, interesting is a YM player optimized speed. This is the kind of file we generated. If you select that, then some files are copied to the lib directory and to the include directory. This is actually a pre-compiled object file, if you want to call it that, of the YM player. You can use it out of the box if you include this header file to your C sources. This is what we do now. We include the player.h file, and this include directory is within the standard include path, so we can use this smaller, greater signs, don't know what you call it in English really, to include. Also, we should include our data for our actual YM file. Just copy that. So, if you go into this .h file, you see how to play it. It's an example. You can call YM sound. This actually generates the sound data. Just copy it. Do sound. This do sound actually passes all the generated YM data to the sound chip. And at some point we actually have to initialize the player, which we can use this one here. If you use this construct over here, it's repeated. Well, we might as well copy that. Do that here. Now this is not the correct name. Beast Data 1 Data, Beast Busters. This is another YM file, just used for the as an example. What we have to use is the one that is supplied by the .h file of the actual generated YM data, and this is this one. A First Division 1 data. Don't ask why it's called that, just use it. We place it over here. Man! So now, if I didn't do anything wrong, pretty print, if I didn't do anything wrong, YM file should be played. Isn't it wonderful if there's no error? So, just for your... okay, be quiet now. For your information, the actual what you see when we did as a pop-up over the lib directory actually is generated. If you go to the C directory, go to pair C directory. Within this directory, all files that were provided by Per Johansen is located, and also a directory called Vide. Within this Vide directory, there's an include and a lib directory, and within the lib directory, all object files of available, well, what should I call it, translated assembler sources that I provided for Vide are located. And the actual lib pop-up is generated from all LST files contained within this directory. So what if you call the pop-up and selector entry actually does is copy the files according to the pop-up from this directory to your own lib directory, and the include file of the corresponding file to your include file. And the final compile you do for your own program just links these sources over here with your bin file. That's a technical view of it. As an example, I will do the same for AIFX file, so well, that you get used to it and you know how to use it. Again, we add a AYFX file with add file. Now it's not a YM file, so we go to a different directory. It's also in the download directory if you downloaded them, and within there the SFX collection, demo, and Aleste_1AFX as an example. So we take that. It's now included within the directory here. Now the pop-up menu build Vectrex AEFX is highlighted and you can use it. You can do that now. And you see, if you watch really quickly, now 2 additional files are generated within the source directory. The Aleste_1s, this is the actual sound effect file. Again, in a not ASCII format, but in a AS6809 file format. And again, a .h file is generated with the corresponding data. And again, we can use the lib directory AYFX player included. Now we've got the AFX player H and the lib files within the object files within the lib directory, and we can play the sound effect. We can do that here. This is again an example. We can just copy it. This is what I will do. We have to include the AFX player. This is the first thing I include. Where is our main file? There's our main file. Again, it's within the standard include directory. The example is, well, not 100% correct. And include the H file. Oops. The H file. And how do we play it? Do sound is the same. We already did that, and we only want to play it if a button is pressed, so we do it like that. We can copy it here. Just have to cook. This is, oh, look at that. I think that is already the correct name. Aleste.1. Where is it? Why doesn't it open the file? Stupid you. Yeah. Okay. Don't know what happened. Anyway, I think this is the correct name. We do it. Button pressed. This for this to work, we actually have to ask for the button. There's a controller.h file. Now we can use it. We have to call check buttons, otherwise we can not access this information whether a button is pressed or not. Actually, for now I will comment out the YM sound, otherwise you will not hear, well, hardly hear the sound if the button is pressed. Let's compile. Well, there's a error, implicit declaration of function check buttons. Now, finally, we got an error. If you double click the line, it will show you the line where the error occurred, and it occurred because we did not include the controller.h file. We should do that. Otherwise, it's no wonder it doesn't know that such a function exists. Controller.h. And run it. Now it knows everything and it might work. You might not see it, but right now I pressed button 1 and you hear the Oleste_1 sound. We can also at the same time play the YM sound, but the thing is you can hardly hear the button press sound. Okay, this is actually quite logical that you don't hear it, because the YM sound data is generated after the AFX sound and such overrides the sound. If we generate the YM sound before the AYFX sound, it's not overwritten and we might actually hear it. Well, it's distorted, you can't really well hear it. Okay. So, I'm not going to bore you with all the examples. As you see, you can add ARCOS player files, AYFX file, we already did that, print sync lists generated files, other sync list files generated from the Vectrex, the scroll, the Vectrex Frogger scroll, that is, different YM file players, 3D for C, these are the demos I showed you before with the 3D stuff, and these are actually all kind of assembler functions that I translated to use with C. You can do that on your own. I will not show it here, perhaps I will do something like that later, but not now. But it's described in the help. In the help there's a whole section for C files, programming in C. As you can see, there is much you can read and so on. Everything I said here is probably described over there, and probably even more. Well, is there anything else? Yes, one small thing. Actually, if in the properties in the C project C debugging is enabled, you can there are some debugging functionalities enabled that you might use. You can only debug C files, or you always can use Dizzy to debug. But additional information for debugging is only generated for .c files and only for .c files which are compiled directly. So if for some reason or another you would include a .c file over here, debug information would not be included. Only for directly compiled C files additional debug information is generated. For information if this debugging is enabled, internally another compiler stage is called, and for some strange C sources there might be errors if compiled with these debugging options and not if debugging is disabled. So if for one reason or another with the debugging options errors are displayed and for without debugging options not, well, then just don't debug. Tell me and I'll look after it. I tried my best, but I can't promise anything. So anyway, for default C files debugging information is created, and you can use the editor Vide to enter breakpoints, for example. We can do that. Breakpoint here, run it. Oops, for one reason or another, this is stupid again. Well, this is a bad example actually. For some reason or another, for line 71, the breakpoint could not be committed. we have to look at it. We have to look at the generated files later. For now, I just use line 71. So now the breakpoint is set. Debugging is enabled, and we have to look at Dizzy. Now you see in Dizzy, if you open Dizzy, you see the C source code displayed in dark blue and yellow foreground letters. You can scroll, you see the more or less complete C source code, and you see the breakpoints that are set on the C source code. But you also see the assembler source code generated, or the assembler source code is now within Vectrex in ASCII format, not in AS6809 format. For one reason or another, I think it's a bug, I will look later at it, for print string D, no source line is generated. I don't know why yet, I have to look at it. But anyway, you see that the C lines are all printed within here, and you can step and debug normally. Actually, this is all there is to C debugging. You can see the lines, and you can enter breakpoints, and not much more is available. You can certainly see global variables. Variables are defined as all C variables are defined with an underscore, so you do not see them directly, but you have to look for them for an underscore. And local variables are located on the stack, and for some reasons I'm not explaining here, it's not very easy to locate or to uniquely identify stack variables and show them. You can see the registers here. There's a new stack stack thingy here. And you can look at the stack, but well, yes, you can debug through it and do stuff. Okay, with this stumbling I'm doing right now, I'm going to finish, and wish you good luck with your C experiences in Vide. Bye bye.